Superscores SS. Empower Your Dream presents. Welcome back, NEAT aspirants, to another high-yield explainer. I'm absolutely thrilled to take you on a journey into nuclear physics today. We're going to unpack the exact physical laws that dictate literally everything, from how stars burn in deep space to the absolute limits of our own engineering capabilities right here on Earth. Let's get right into it. Here is our high-yield roadmap for today. We'll quickly move through mass defect and energy, hit the binding energy curve, break down fission and chain reactions, and then heat things up with fusion and plasma physics. Finally, we'll wrap up with the Lawson criterion and the cutting-edge world of fusion-fission hybrids. All right, Section 1, Mass, Defect, and Energy, the foundations. Okay, let's dive into this. To really grasp atomic energy, you've got to understand a totally wild concept. A nucleus actually weighs less than the sum of its parts. Seriously. If you were to put the individual protons and neutrons of an atom on a tiny scale and then weigh the fully assembled nucleus, you'd find the assembled one is lighter. We call this missing mass the mass defect. But look, that mass didn't just vanish into thin air. Thanks to Einstein's E equals mc squared, we know that mass gets converted into an unbelievable amount of energy. It becomes the strong nuclear force, and it has to. Because without that intense binding energy, those positively charged protons, which absolutely hate being next to each other, would just blast the nucleus apart. So, let's look at the strict math for carbon-12. This is a classic high-yield example for you guys. A carbon-12 nucleus has 6 protons and 6 neutrons, right? Well, an isolated proton is about 1.007 atomic mass units, and a neutron is around 1.008. If you multiply those out and add them all up, the constituent mass is actually significantly greater than the actual mass of the assembled carbon-12, which is defined exactly as 12U. Doing the subtraction, that leaves us with a mass defect of 0.0989U. When we multiply that missing mass by 931.5 MeV per U, boom, we get a total binding energy of 92.2 MeV. That is the exact amount of energy you would need to completely rip a carbon-12 nucleus back into its individual pieces. Moving right along to Section 2, the binding energy curve and the stability of elements. Now, what's really interesting about this curve is how it perfectly maps out the ultimate destiny of basically every atom in the universe. We're looking at binding energy per nucleon plotted against mass number. Check out that peak right around a mass number of 56. That is iron 56. It boasts an average binding energy of about 8.8 MeV per nucleon, making it the most stable form of nuclear matter in existence. It's the absolute king of stability. Because nature is always lazy and seeks the lowest energy state, lighter elements way on the left, like hydrogen, are desperately driven to combine or fuse to climb up that curve and release energy. On the flip side, those massive, unstable heavyweights on the far right, like uranium, well, they gotta split apart or undergo fission to move back up toward that iron peak. And that brings us to Section 3, Fission and Chain Reactions, splitting the heavy giants. Imagine a relatively slow thermal neutron cruising along until it strikes a uranium-235 nucleus. The uranium absorbs it, temporarily turning into a highly unstable U-236 compound nucleus. This thing violently oscillates for just a fraction of a second before literally snapping into 2 lighter, much more stable products, often krypton and barium or xenon and strontium. As they snap apart, they release a massive 200 MeV of kinetic energy and, crucially, spit out 2 to 3 extra free neutrons. So how does this one event build into a massive, continuous power source? The fission chain reaction sequence happens in 4 distinct steps. First up, neutron absorption by a heavy fissile nucleus. Second, the immediate chaotic instability of that newly formed compound nucleus. Third, the physical division into 2 lighter fragments releasing immense energy. And finally, step 4, the release of those secondary free neutrons. Those secondary neutrons act as the spark for the next generation of atoms, kicking off a continuous, self-sustaining chain of splitting nuclei. So the crucial point here is, how on earth do we control this without causing a massive explosion? Well, for a chain reaction to sustain itself, you need a critical mass. For U-235, that's a dense sphere of about 15 kilograms, literally just the size of a tennis ball. We track the stability using the multiplication factor, or the K factor. For steady, continuous power, K must equal exactly 1. If K creeps above 1, the reaction grows exponentially. But here is the most high-yield fact for your exams. Only 99.35% of those neutrons are released instantly. The other 0.65% are delayed neutrons, emitted seconds later by the decaying fission products. These delayed neutrons are total lifesavers. They magically extend the generation time from a hyper-fast 25 microseconds to a very manageable zero point 0.1 seconds. That gives our mechanical control rods the actual physical time they need to absorb neutrons and keep the reactor safely under control.
All right, Section 4, Fusion and Plasma Physics, Combining Light Nuclei.
Let's quickly contrast these two mechanisms. Fission is all about breaking apart unstable giants to get roughly 1 MeV per nucleon. But fusion forces ultra-light elements together. Because hydrogen sits way at the bottom of that binding energy curve we looked at earlier, fusing it yields way more net energy per unit mass than fission ever could. It is insanely exothermic. But it requires overcoming some seriously difficult initial conditions.
To make fusion happen, we basically face a literal mountain that our nuclei have to climb. Protons have a positive charge, right? And like charges fiercely repel each other due to electrostatic forces. So, the big question is, how do we smash positively charged protons together without them violently pushing each other away? Well, this intense repulsive force is what we call the Coulomb barrier. To completely conquer that Coulomb barrier, we have to strip the atoms of their electrons by cranking up the heat. We're talking up to 100 million Kelvin. This creates a superconductive ionized cloud called a plasma. In this ultra-hot environment, the bare nuclei are zipping around with such intense kinetic energy that they slam into each other, closing the distance to about 1 femtometer. And guys, at exactly 1 femtometer, which is just the diameter of a single proton, the attractive, strong nuclear force finally wakes up. It violently overpowers that electrostatic repulsion and fuses the nuclei together.
The most heavily researched reaction for commercial fusion is the deuterium-tritium, or DT reaction. We take 2 heavy isotopes of hydrogen, deuterium, which has 1 proton and 1 neutron, and tritium, packing 1 proton and 2 neutrons. When they fuse, they form a super-stable helium-4 nucleus, an alpha particle, and they eject a single incredibly energetic 14 MeV neutron. That flying neutron is the golden ticket. It carries the bulk of the kinetic energy that we want to capture as heat to generate our electricity. This takes us to Section 5, the Lawson criterion, ignition conditions.
As you can imagine, maintaining a 100 million degree plasma is no walk in the park. Enter the Lawson criterion, first formulated by John Lawson back in 1955. And this brilliantly illustrates that for a reactor to achieve ignition, meaning it generates net positive energy, the fusion energy produced has to outpace the energy lost to the environment. It all boils down to the triple product: plasma density multiplied by temperature multiplied by the confinement time. It's a strict thermodynamic balancing act. If your density drops, you've got to drastically crank up the temperature or the confinement time to keep the reaction alive.
And finally, Section 6, Fusion-Fission hybrids, the best of both worlds. Because pure fusion ignition is just so incredibly tough to maintain, engineers are now looking at combining both sides of the periodic table in a fusion-fission hybrid reactor. The genius idea here is to take those super-fast 14 MeV neutrons flying out of the fusion core and let them strike a surrounding blanket of standard, non-fissile uranium-238. These fast neutrons have so much kinetic energy they actually trigger fission in the U-238, multiplying the energy output of each fusion reaction by 10 to 20 times. Plus, since it totally relies on the fusion core for those neutrons, it's a subcritical reactor, meaning it can literally never melt down. But as always, the engineering challenges are just immense. Bombarding a structure with 14 MeV neutrons causes severe atomic displacement. You'd need hyper-advanced materials, like tungsten-armored RFM steels and high-entropy alloys, just to survive that brutal environment.
As we speak, the Chinese Academy of Engineering Physics is actually constructing a massive Z-pinch fusion-fission reactor with a highly aggressive goal of commercial power production by 2035. Could combining the brute force of fission with the clean elegance of fusion finally solve our global energy needs? It is a fascinating engineering frontier for you guys to keep your eyes on. Thanks for watching SuperScore's SS Presents.